going to finish it off. We're going to do the grand induction. We're going to prove the Zergel conjecture. But first, I'm going to start with an example to remind us of Rouquier complexes and what we're really doing. Okay, so example reminder. So the reminder is going to be the Rouquier complex of TSUT. So we have type A. And we're going to remind ourselves with what T, Fs, Fu, Ft is. So this is going to be this big complex where in each term we have the number of ways to leave out I of these things. So in the first step we leave nothing out. So we just have Bt, Bs, Bu, Bt. And I guess if there's one piece of colored chalk. So then in the next step, we have all the ways to leave one thing out, right? Bt, Bs, Bu, Bt, Bs, skipping Bu, Bt, Bt, Bs, Bt, and then Bs, Bu, Bt. And I'm not going to do this forever. I'm just going to look at the first couple terms just to make a point. So in the next step, we leave out BTBS, BTBU, BTBT, BSBU, BSBT, and BUBT. And then the next one has 4 terms, and then the next one has 1. So the key point here is that what we want to do is take this guy and write him in terms of the indecomposable Zergel bimodules. We already know how to do this in all of these examples. So in fact, I was going to do this. Actually, the color chalk isn't so significant. This thing is in fact just BTSUT. This is one of these calculations. This is one of those weird Kazdan-Lustig polynomials where there's interesting lower terms, but this guy doesn't actually break off. And then whenever you have 3 distinct colors appearing, and it's going to be nothing interesting you can do. So this is just BTSU. Whereas BTBUBT is, as we know, going to the dihedral relation. This splits into 2 terms. So this is great. Okay, don't worry about it. It's not a big deal. So this is BT, BU, BT, and BT. Whereas this is BT, BS, BT, and BT. And then this is BS, BU, BT. Now you should remember that everything in this row has a homological shift by 1 because we're in grading degree 1. Everything in this row has a homological shift by 0. Everything here is a homological shift by 2. Okay? So now, again, here we write it in terms of the indecomposable Zergel bimodules, and nothing interesting happens until right here when BT splits into things with shifts. Okay, and I guess since we're basically done, I might as well write the next step. BT, BS, U, BT. Okay? So again, if you don't want to write down this whole example in your notes, you don't have to. But the point to be made is this, that lo and behold, there are some terms of shifts that appear. This can't be avoided. We're dealing with the Bode-Samuelson. Bode-Samuelsons have shifts. But miraculously, right, there's maps between these things. And there's some non-zero map from, I guess, one of these BTs, or even some linear combination, to this guy here with the shift. So this is overall shifted by 2 with a -1. This is BT with an overall shift of +1. This is BT with an overall shift of 1 +1. And there's a contractible summand in there somewhere. So that this and this will cancel. Right? And after you cancel these things, it's hard to figure out what the maps are that remain in the complex. But if you don't care about the maps in the complex, and you only care about which summands appear, you can just cross them off. And similarly, this bt with the plus 1 also cancels that out. Okay? And when we're done, everything is in the diagonal shift. In homological degree I, or in shift I. So this is the diagonal miracle. Which, if you recall, was something that we proved assuming the Zergel conjecture for all the terms involved. Okay, now we didn't actually prove it. I said it was technical and not that exciting, but it is something that you can assume. So, and again, I just want to do this calculation for you so you see how to build this up slowly. Okay? Here's one step. And this thing, after I crossed him out and crossed off all this stuff, is the so-called minimal complex. Okay? This is F CSDUT min. Okay? There's certainly no more terms you can cross out. Once we've crossed off every term we can, then we end up with the minimal complex. And this shouldn't depend on the reduced expression that we chose. That is, it should be up to isotopy, up to homotopy independent. So the next thing we can do to build this up and find the next one is take this minimal complex and tensor it with, say, Fs. Okay? This should go and make everything Fs increases the size of this thing. So we should get some things that are bigger. Remember that Fs is Bs goes to R shifted by 1. So the terms in this overall complex, there's going to be twice as many. You're going to take every original term and multiply it by Bs and keep it in the same spot. And then you're going to take every original term and move it up to the next spot. Okay, so there's two halves of this. So the first thing we do is take this and multiply by Bs. And this is a calculation that I believe you did on the decategorified level in the Heck algebra. But since we're assuming the Zergel conjecture for everything involved, you know that that works on the categorified level. Okay, so I'm going to cross this off to remind ourselves it's being replaced with these. And then we have to, multiply these things by Bs. And I'm only going to do a couple steps, but you'll see what happens. Right? Every term I'm multiplying by Bs, yes. And BSU, TS, and BSU. Thanks very much. Okay, so when you multiply this guy by S, it brings us down, so we get 2 copies. And same with this guy, so we get 2 copies. When we multiply this by S, it brings us up, and there's no lower terms. When we multiply this by S, we get BTS. And when we multiply this by S, there's we go up, and then we get 1 lower term. And so forth. But then we also have taking this guy and bringing it up. Et cetera, et cetera. Okay? And now we can make some distinct points. Okay? I'm not going to take all of these and multiply by S, but I will draw the stuff below the line. Everything here gets brought up here. Okay. And then there's the rest of the calculation. So there was another part of the diagonal miracle, which says that when you take the minimal complex of this guy, all that's left in degree 0 is the indecomposable you cared about. But as you can see, these other things are exactly canceled off by those. And of course, all the positive shifts should cancel out too. But the fact that the positive shifts cancel out is really clear. Because we took something for which S brought us down. Okay? And we put -1 and +1 here. But then we also took the same guy and put it down here, so that there's available a copy of him to cancel out. Makes sense? So the +1s always easily match up to things below the line. And so the fact that this is actually a non-zero map is actually very straightforward. This is just what happens when you take BS and tensor with this complex. Right, so that you can do in a very explicit way. But the magic, this is the magic, that all the minuses do cancel out. Okay? The fact that the pluses cancel out is this, so the fact that pluses cancel out, this is the so-called fact that this complex is in, I don't write min, sorry. I guess in my notation I was writing this without an underline to indicate the minimal complex, and this with an underline to indicate the Ruquier, the original Ruquier complex, because it depends on the expression. So the fact that the pluses cancel came from the fact that the minimal complex is in this k less than or equal to k bigger than or equal to 0, which is the statement that all the shifts that show up must be in, that sort of any expression, but using only positive braids, that any shifts that show up must be negative. No positive shifts show up. So this is just a general statement that I said was an exercise. And the exercise really is just taking this and tensoring it with BS and seeing what happens. But the fact that the minuses cancel, this is really something special about reduced expressions, and this is the diagonal miracle. This is the thing that's actually interesting. Okay. So our goal is going to be trying to use the structure of these Ruquier complexes to deduce the Hard-Lefschetz property. I'll remind us of this. And to deduce the Hard-Lefschetz property on this entire thing here, right, on BWBS. Okay? So this entire thing here embeds into this entire thing. And it's essential that it includes the stuff in negative degree. Okay? I mean, that's clear. So we will be using we can't just use a straightforward argument that we have a map to something that has the Hodge-Riemann bilinear relations. These things all have the Hodge-Riemann bilinear relations. This is something with a shift. So we need to be able to deal with that. And you'll see it come up in the argument. I just wanted to point it out now so that it's in your mind and isn't too confusing when it happens. So let's go over the grand induction and what I'm going to do. So, grand induction. The term grand doesn't just mean like we like it ourselves. It means that we're inducing on like 8 different things at once that all imply each other in a big cycle. That's usually what people mean. Okay. So we have a summand of the Bose-Samuelson module. What did I change from W to X? W. And the right quotient has its induced form, induced from this being a summand in that thing, which has the nice multiplicate form. And it has this Lefschetz operator, which is left multiplication by row. Then we could look at BWBS. Apparently in my notes, it's BX. Oops. This guy is inside this Bose-Samuelson, it has an induced form. And we have these Lefschetz operator, L sub zeta, which was left multiplication by rho plus doing nothing to the W part, and then left multiplying by rho. So multiplication, by zeta rho. All right, so this is multiplied by zeta rho to the left of the BS. Okay, so let's see. So what we wanted to show was a bunch of things. We wanted to assume a bunch of things about W and prove a bunch of things about WS. Okay, so we're going to suppose everything.
Can you please just explain the L zeta once again? Maybe in terms
Right.
of picture.
Yes. In terms of the picture, this is rho multiplied by WS on the left plus doing nothing, and then rho, and then zeta rho, and then S. This is a very annoying algebraic notation. Okay. So we're going to suppose everything is true for stuff less than WS. I suppose I should mention that WS is bigger than W. Okay. So we had this argument that if we had a hard Lefschetz, I need to stop writing X. For W, so remember this indicated that this space, sorry, with the zeta, that this space with our given form had hard Lefschetz. Okay, that this finite dimensional right quotient space had hard Lefschetz. But if we knew this for all zeta bigger than or equal to 0, okay, then by a limiting argument, that is by continuity of Hardy-Riemann bilinear relations, and the fact that we knew HRXS for zeta bigger than very large, so that these two properties combine to getting Hardy-Riemann bilinear relations for all zeta bigger than or equal to 0. And then, by setting the actual case we cared about was when zeta was 0. This is just the Lefschetz operator of multiplication on the left. But now we have Hardy-Riemann bilinear relations for that. And using the fact that the local intersection form embeds into the global intersection form. Yes. So you notice every single time, it's because my notes have X. Should I make it X or W? I'll make this mistake 8,000 times. What should I do?
We just declare W to be X and then it doesn't matter.
Okay. W is X. I will not use both. But I will try to keep W. I'm sorry. So the fact that this thing is Hardy-Riemann and that embeds in a primitive said that this was not a degenerate, that everything that was supposed to split off should split off, and that gave us the Zergel conjecture for WS. It has the right size. And then, because it embeds inside something with Hardy-Riemann and is the right size, it also has hard Lefschetz on Hardy-Riemann. And so all we need to, we had reduced to this. This is what we did last time. Now we need to finish the loop. We need to assume that we have, well, we need to get here, basically, assuming that we have all these things for less than this. So to finish the loop, what do we have? We have the Zergel conjecture for things less than S. And this was enough to imply the diagonal miracle for smaller complexes. So we have the diagonal miracle for less than WS. For FW. Okay? This is not FWFS. We're going to get there. But at least we have the diagonal miracle for FW. Okay? So if we take FW and the jth homological degree, okay, then this is going to be a direct sum of a bunch of BZs shifted by J. Okay, this is great, and also FW0 is just BW. So what we're eventually going to do is take this guy and shift it back by minus J so that we get something that's really in degree 0. Something that's perverse. Okay? Now we also have a whole bunch of Hadrimon properties for every summand that shows up inside here. So we're going to use that to prove something which I'm going to call Ruquier Hadrimon. And that's going to be the statement that if we take FWJ and shift it back by minus J, so that now it's really something which is a sum of indecomposables with no shifts, it could possibly have Hadrimon. And this satisfies HR and HL with respect to left multiplication by rho. All right, there's no S here on the right yet. You know, everything is still just inside W. So there's nothing to multiply by. There's none of this yet. We're just looking at left multiplication by rho. And the induced form. Right? So the point is that FWJ is inside this direct sum of Bott-Samuelsons, where you weave out J terms. So it's always to leave out J terms. And so each of these has a form, and so you look at the induced form, and these things have that. Okay? So we know that individually, by this condition, that each thing has Hadrimon. But we need to know that it has a Hadrimon with respect to the induced form from these particular things. It's not a big deal, but it's something that's sort of fairly straightforward. So we'll talk about how you prove this in a sec. And then we're going to use the fact that we already know that if we have anything less than W and we bump it up, that it has the Hadrimon bilinear relations with respect to zeta. And knowing this and this, we know a ton. Know enough about taking FW and then multiplying by FS to deduce HL WS theta. Okay, so this is going to be sort of the argument. We kind of want to fill in these missing gaps, discuss this, and then talk about how we know enough. All right. Going back to this example, here's this thing, and we know that all these guys have Hadrimon when you shift them back into degree 0. And then here's this thing, and we know that everything here has Hadrimon, or at least these are the terms where it went up and down. That's not counted, okay? But every time it went up, it has Hadrimon, and every time it went up and down, it sort of magically cancels out. We haven't proven that yet because we don't have the diagonal miracle for that yet, but that's going to be part of what we show, okay? So all these lower terms have Hadrimon, and you basically just remains to show that this term has Hadrimon. So this is going to be the grand induction. All right. So now I need to explain to you how we show this Ruquier-Hadrimon business. And why one can get hard Lefschetz out of Hadron.
So one question.
Yes.
So when you define the Rukier-Hodge-Riemann, can you just tell me the meaning of the notation that is right after the defined sign? FWJ.
So FWJ is this jth homological term.
Right.
And then we shift it back so that it's in degree 0. So, when I was writing all these examples, I didn't have shifts everywhere. I put the big shift on the top, and I'm just canceling out the big shift at the top. Okay. So this is a good example of the kind of methods we use here. So if we assume the Zirkel conjecture for everything less than or equal to W, and the Hodge-Riemann bilinear relations for everything strictly less than W, but when we bump it up by S, that this implies the Rukier-Hodge-Riemann bilinear relations for W. And remember, there's no zetas here. We haven't bumped it up yet. Okay. So, and this is, remember, really a statement about the degree 0 term. Okay. So FW is going to show up as a summand complex of FYFS for y being for ys equals W. All right, so there's some S for which is, I'm not taking a fixed S. I'm saying for all symbol reflections. So there's some symbol reflection that brings us from some smaller term up to W, and therefore FW is a summand of this tensor product. Okay. So that means that the jth term of FW, well, this shows up inside two terms. What are the two terms in this? Remember, there were two halves. Okay. There were the terms that we took something in Fy and then multiplied by Bs and didn't change the shift. So sorry, let's put a minus j everywhere just to be annoying. Shift it back to degree 0. So we took something in Fy and we bumped it up and we didn't change which degree we were in. And then we also took something in Fy of a lower degree and just moved it up. Okay? So I think this is correct. Yeah. I mean, it's going to be the thing that's perverse, right? So this and this should cancel out. Okay. So we have this guy that we're interested in. We want to show that this guy has the Hodge-Riemann bilinear relations. He's a summand of something which does have the Hodge-Riemann bilinear relations and something which doesn't. Okay? So this guy has HR by Rukier-Hodge-Riemann bilinear relations for Y. Okay? And this thing doesn't. But let's look at this thing. Okay? So Fy j minus j is a direct sum of a bunch of BZs. Okay? It's by the diagonal miracle. We've shifted it back, so it's just a bunch of things with no shifts. And what I'm going to do is I'm going to split these in two. Where B up I mean, I guess I can put that in here. Sorry. I probably should. Good question. Okay. So remember that there were two kinds of terms, the terms that went up and the terms that went down. So B up is going to be the direct sum of those z's for which z goes up. And B down is going to be the direct sum of those z's for which z goes down. So that when we investigate this term, what happens when we multiply by bs, then it's nice and straightforward. We take b up and multiply by bs, and then when we take b down and multiply by bs, we get two copies of b down. Okay. And our Lefschetz operator commutes with this splitting, because the Lefschetz operator is just the left multiplication. So this will be a problem later when we have the zeta and we have bumping things up. But for the moment, this direct sum decomposition commutes with L. Okay? So this term here is the direct sum of a bunch of things of the form BZBS, where z is less than w. And so using this thing has HR. Wonderful. So then we have to deal with these terms, okay? But the great fact here is that, and this is another one of these exercises, that, okay, so we have this guy here, which we know has no shifts, okay? And he's mapping into something with shifts. Right? Well, there's no maps of negative degree between things without shifts. So in fact, there are no maps to here. Okay? So the image lies entirely within this part. Did I say that backwards? There's no maps to here. The image lies entirely within this part. All right. This is where you shift it up by 1, right? So that you, right. Okay? No maps to here. Okay? So I mean, there's many different arguments you can make to deal with this. The other fact is that here is a guy that had Hadrimon shifted down. Well, that can't possibly have a non-zero form. So this is another one of the exercises I gave, that if you have something that has hard Lefschetz and you shift it down, then the Lefschetz form, the Lefschetz pairing, must be 0 now. If you shift it up, this isn't true. But if you shift it down, there's no way to have a Lefschetz pairing on that that's non-zero. Okay? In other words, you have to apply L too many times, you're going to get 0. Right? You're applying L the right number of times to already something which is L of a primitive rather than to the primitive. Okay, so you're applying L1 too many times here. So the Lefschetz form is 0 here. Okay? So what I'm trying to say is that if you take the map from I wish the board were a little bigger. So you have this map from FWJ minus J, this thing that we care about. And he maps to two terms, this sort of nice one, J minus 1. And then you've got this other term, B up BS. And then you've got these two nasty terms. And then you project further to just the first two things, the ones which we know are nice. That in fact, this projection, here we have a map, which is an inclusion of a summand. Okay? And then, in fact, it projects to this thing. But that, regardless, this is still an isometry. Right? That if you project from here to here, as far as the image of this is concerned, you haven't changed the form. Okay? In fact, this will still be a summand of that. Okay? I guess this is an argument I don't have to make, but I'll need to make it later. That, as I said, there's no maps to this thing. And the maps to this thing are like maps of degree +1, but since there's no maps of degree -1, they can't be inclusions of a summand. They're sort of in the Jacobson radical. They're in the maximal ideal. Right? There's nothing that can split out of here. So in fact, the projection to just these two parts had to have been a summand in the first place. It can have a non-zero map here, but really, once you subtract things, it's really the map to here that counted. Okay? So this overall map, here to here, this map is an isometry for the Lefschetz pairing. Okay? And it's actually an inclusion of a summand. Inclusion stable summand, L stable. So a summand inside something with Hadr-Riemann has Hadr-Riemann. Okay. So the basic idea, the trick here, was that we have something that we want to show has Hadr-Riemann. It embeds inside something which doesn't. But we find some way to ignore the terms that are annoying. So we split into nice terms and bad terms and ignore the rest. So this trick will repeat over and over and over and over and over again. And we'll get a little bit, there will be one little extra bit each time. But this is the key idea. All right, it is tricky. I won't deny it. Okay. So we've shown the first step. So the second step is to sort of figure out what this has to do with hard Lefschetz. Okay? And, let's just quickly remind that so the reminder is that left multiplication L zeta on BSWS had a nice form, right? We viewed it as left multiplication by rho plus zeta rho here, but then we could break things through. And so this was actually a sum of some coefficients. I'm trying to remember, I think I called them z. I'm going to call them lambda I. Times sort of breaking the ith strand. Okay? And that, as a result, plus something in the right, something that we don't care about. Something that contributes nothing once we take the right quotient. And that all these lambda i's were positive. and at least one of them is strictly positive. Okay, but they're all at least non-negative. And so we have this wonderful, actually, no, they're all strictly positive. Strictly positive, for what it's worth. If we think of this as sort of, if we cut this in half, we can view this as two adjoint maps to some smaller terms. Okay? So let's do that now. We're going to take BS, WS, okay, and map it by sort of the direct sum of these terms here to the direct sum of all ways to remove one term from WS. So this direct sum, okay? We're going to take the intersection form here. And over here, we're going to rescale the intersection forms by this positive number. So when you rescale a form by a positive number, you don't change any of the properties, hard Lefschetz, Hodge-Riemann. Okay? So this sum, this has no coefficients, but we just changed the form over there. Okay? And so the claim, let's call this map sigma, is that the pairing of sigma v with sigma w, we needed to do the hard pairing, is equal to the pairing of v with lw. L zeta w. We could take two things here and send them here and pair is the same as the original, right? Or in other words, that the sum of lambda I times applying this thing to v and that thing to w is equal to the sum of v with lambda I, that thing, w. Sorry, right. Because this sum is v with L, w. And this is straightforward, okay? I mean, these are adjoint maps, and so you expect this to be the case. I mean, I claimed that a junction was the same thing as flipping diagrams upside down. But, you know, I don't think I ever actually proved that. Although, on the other hand, this is an easy enough exercise, right? If you think about v as being a bunch of polynomials in each spot, okay, then all this does is multiply these two together. And all this does is multiply these two together, okay? So that when you multiply them, you sort of multiplied all the polynomials in v with all the polynomials in w, and merged the ones in these two slots. Then you have to shove it all to the right and find the coefficient of C top. Okay? So you need to shove it through every strand except the ith strand, basically. Whereas here, you're doing the exact same thing. To pair these two things, you multiply the polynomials against w, you merge the polynomials that are in this spot, and you compute the coefficient of C top. Okay? Now here you are computing the coefficient of C top in one fewer strand. Here you're computing the coefficient of C top with one more strand, but you put CS there. So it sort of didn't change the computation in the slightest. You get the exact same numbers. So this is a fairly straightforward fact. Okay. So that's the start. And remember that we had this proposition that said that if sigma was injective in negative degrees and the right-hand side had Hodge-Riemann, then the left-hand side has hard Lefschetz. Okay. Well, sigma is not injective in negative degrees, but once we pass to minimal complexes, then it will be. Okay. So I'm going to state the big theorem, and then we're going to prove it in 3 steps. So that if we have the Rukiya Hajiman by iterations in W, I said that we should know just about everything about this thing. And also, we had this previous statement, which I'm just going to include as part of this theorem because it's an important part of the induction. Oh, yep, I will put an X there. Ha! That was on purpose this time. Actually, maybe I'll put a W here. I'm sorry. Okay, so we can assume this to be true for all things less than W. We want to show that if S increases us, then we have hard left sets for any zeta bigger than or equal to 0. Whereas if it decreases us, we had this just general proof. We already proved this, that if it decreases you, then so long as zeta is non-zero, you have hard left sets. So the proof will come in two different cases, when zeta is bigger than 0, when zeta is equal to 0. They are really two completely different situations. Okay? The reason we need both of them is so that we can use the continuity argument to get from the fact that we know hard left sets, hard Riemann for really high numbers, to bring down to hard Riemann at 0. But the hard left sets is two cases. Okay? So the first statement is the case zeta than 0 and ws less than w. And this wasn't anything about Hadj-Riemann. This was just this exercise. Okay. That is, you fix a basis and you compute. It's very straightforward. Part 2 is going to be the first interesting case. So if zeta is bigger than 0, okay, and we repeat the same argument. Okay, we have the diagonal miracle for FW, which says that FW in degree 0 is just BW, and that FW in degree I mean, this map is going to be essentially the first differential in the Rukiye complex.
So you say etc. That means you are going to assume every single thing up until now.
Yeah, I suppose you can figure out precisely what it was that we used, but it's too much trouble. So this map is going to be the first differential in the Rukiye complex. So let's just investigate the first differential. So FW0 is BW, and FW1 is going to be some sum of BZs shifted by 1, which again I'm going to split as B up and B down. Okay? And so we have this map. Now we multiply by BS. So that we have this map FW, FS. Okay, so in degree 0. So what's FWFS is BWBS in degree 0. And then this goes to a sum of terms. You have this thing times BS. So B up BS, B down 1, B down minus 1, and then BW itself just brought up. Okay? But this is a map of, so here's the difference. When you were earlier doing this argument, we were interested in summands. Now we're interested in a map of degree 1. Okay? Legitimately, everything up here is actually shifted by 1. Okay? And this map here is some summand of sigma. Okay? I mean, I'm going to still call this map sigma, but it's not really this map here. It's the induced map on summands. Okay? Now, unfortunately, this splitting does not commute. Okay, so sorry, I shouldn't split it anymore, sorry. Sorry. This is B down BS. Okay, so the splitting of B down BS into BS plus 1 and BS minus 1 does not commute with this Lefschetz operator. Okay, because we put some junk. It's not it's a bimodule splitting, but not a module splitting for any polynomials in arbitrary places, and we exactly put zeta rho in the wrong place. Okay, but by part 1, even though this is the sum of things that go down, zeta is not 0. So even though things go down, it still has hard Lefschetz and hard Riemann even.
Sorry, what?
You know, this is the sum of things that go down. Okay? And this is the case that goes down. We've already shown that it has hard Lefschetz. Right. I'll say it has hard Lefschetz, and that implies hard Riemann as well. Okay? So this has, but nonetheless, has HR by part 1 for the various lower terms. Okay? And this thing has hard Riemann by induction. And this thing has hard Riemann. And finally, sigma is injective in negative degrees. So, do people remember why sigma is injective in negative degrees? In that case, I'll put an exclamation here and explain it. Okay? Why is this good enough? It's because, so, you know, we know that FW, in general, FW, or just, so we know that FS, in the derived category, is just RS shifted by minus 1, shifted up. Okay? So FW in the derived category is just RW shifted by minus the length of W. Right? In other words, this complex is exact everywhere except for the very first term, and we know what the kernel of the map is. Okay? So kernel of map is generated in degree plus the length of W. Okay? In fact, not only is it injective in negative degree, it's injective in every degree less than the length of W. Okay? It's injective almost everywhere. Okay? So this is just the argument with actually knowing the cohomology of this complex. Okay? So we have an injective map of degree 1 from some guy to something that has hard Riemann. Therefore, the original thing had hard Lefschetz. So the earlier proposition says HR of the right side implies HL of the left. Hooray. And I guess the point is that sigma also is an isometry, right? Or in this sense. That doesn't change when you restrict to summands. So we have only remaining the hardest case. Well, this is the case where L zeta is just normal left multiplication by row. Okay? And now, we repeat the same, the beginning part of the argument. We have this map from BW, BS to these various different terms. So B up, BS, shifted by 1. Let's see. And B down, now we can actually do the splitting, right? So B downshifted by 0 and B downshifted by 2. And then we have and BW itself. Okay? And because this time L commutes with the decomposition. So now we're going to mix every argument we've seen so far. Okay? We had some argument about how when we have things that are shifted in the wrong place, that we get something in degree that we don't have a problem. Okay? We had some argument with this original proposition that said that Hodgman on the left-hand side implies hard left shifts on the right-hand side. But we're not even going to be able to apply that in this case. We have a whole bunch of different techniques, and we're going to do them all. The point was, we did this argument on the first side, where we said that terms that are in the wrong degree don't matter. Okay? But that was for an inclusion of a summand. Okay? Now we are talking about a degree 1 map. Right? You see that all these things don't have the right shift. Right? Where's the degree 0 part? Actually, it's this thing here. So remember in the original situation when I did TSUT, okay, that we had the term we wanted on the left-hand side, and then these extra terms. And these extra terms canceled out the stuff that went down. Okay? So actually, that's the part where sigma actually maps sort of, picking out summands. Each of these terms here actually comes from a summand over here. So actually, we want this term to survive. We like this term. This guy's good. This guy, on the other hand, because of the diagonal miracle, which we haven't proven yet for this complex, but this guy should cancel out something in a higher degree. In fact, we don't need the diagonal miracle to know that. We already know that. Because this is at least a reduced expression, and so we know that the only shifts that can appear are negative. That positive shifts will cancel out. So this shift will survive because it's supposed to survive because it cancels something out here. But this shift actually is canceled by something in higher degree. Okay, so I'll write this down. Have no fear. So we've got a lot of tricks, but this is degree 1, not degree 0. So it's tricky. Okay? Like these terms matter now, but this doesn't have HR. Or I guess this does have HR, sorry. All right, so let's do it. Okay. So FW, Fs is in k bigger than equal to 0, which implies that only negative shifts, relatively negative shifts, are allowed in minimal complex. Which implies that the B down 2 term must contract against something in higher degree. Something in homological degree 2. And so we can ignore it. Right? In other words, if we just take this map and then project to everything but him, then this is still, it's still going to be a first differential in a Riquier complex. Okay? And it's not even going to cancel out any of this stuff. Okay? So we have BW, BS. Maybe I'll just put the bars on things now. Goes to, let's see, I'll write it all now. this goes to b down 0 plus b up bs plus bw shifted by 1. Okay? So this guy here, each of these has HR by induction. Okay? And this is a map of degree 1, because there's a shift here. So if there were no image here, which there is, but if there were no image here, then we'd be able to use the proposition and deduce Hard-Lefschetz on this side. There is an image here, okay? At least when this thing isn't so we have to isn't small. So we have to deal with this somehow. But now there's two easy cases, okay? So we want to show Hard-Lefschetz, right? So that is, so we pick a given vector v in this vector space in degree minus k, and we want to show that L to the k of v is not 0. Okay? So we're just going to repeat an argument very like the proposition, just with one slight difference. Okay? Basically, I could have made the proposition more general by saying, suppose you map in degree 1 to something that has HR and something that has HR shifted. What happens? Okay? So I'm going to call this component sigma 1 and this component sigma 2. Okay? So if sigma 1 of v is not 0, okay, then we have this map into something, and this guy has Hartmann and HL. Okay? So it's in degree minus, so that says that L to the k of the image has to be non-zero. Okay? L to the k of sigma 1v is non-zero, which means that L to the k of v is non-zero. L commutes with sigma because L is just a multiplication. So that's the easy, and it ended up being easy. So if anything was non-zero here, it's just already done for almost trivial reasons. Okay? But if sigma 1 of v is 0, then we use the proposition. And repeat that argument. Right? If you go to something primitive, then you're done. If you go to something not primitive, you're done. If you go to something primitive, then use HR. That's the original argument. So that was it, actually. This isn't. It's one must keep track of all the degrees and all the inductive things, but the actual proofs aren't that hard. You have a map. You've gone through a long, annoying process to construct a map that you can understand homologically, and where it satisfies this form property that sigma v, sigma w is VLW. And then you just sort of unravel what Hard-Lefschetz and Hartmann give you. So that was it for the proof of the circle conjecture. And my plan was for that to last an hour, and then to take a break, and then to answer any sort of questions. Or if you have no questions, then I'll just talk. But
we will see flat moment then again.